Hello and welcome once again to Stat 761. And we will be going through, we will continue going through the exercises and solutions to the exercises. To this effect, let me go to the right place here. So we will continue with problem 1113. And problem 1113 is asking for an intuitive explanation of why the early exercise of an American put becomes more attractive as the risk-free rate increases and volatility decreases. So the early exercise of an American put is attractive when the interest earned on the strike price is greater than the insurance element lost. When interest rates increase, the value of the interest earned on the strike price increases, making early exercise more attractive. When volatility decreases, the insurance element is less valuable. And again, this makes early exercise more attractive. And so problem 1114, the price of a European call that expires in 6 months and has a strike price of $30 is $2. The underlying stock price is $29 and the dividend of 50 cents is expected in 2 months and again in 5 months. Risk-free interest rates, all maturities are 10%. And what is the price of a European put that expires in 6 months and has a strike price of $30? You use, of course, the put-call parity equation, the one that is extended to also include dividends. So using the notation in the chapter, put-call parity gives C plus K to the minus RT plus D is equal to P plus S0, or P is equal to C plus K to the minus RT plus D minus S0. So basically D is the present value of the two dividends that are paid for, and everything else you just plug in for what it is. The call is $2, K is $30, e to the minus 0.1 6/12, which is 1/2, because that gets paid in half a year. It expires in 6 months. This is the present value of the dividends, 0.5 e to the minus 0.1, 2/12, because one is due in 2 months and the other one is due in 5 months, so 5/12 over here, minus 29, which is the stock price. And you get 2.51. In other words, the put price is $2.51. Explain arbitrage opportunities in problem 1114 if the European put is $3. So what happens if the European put is worth more than what put call parity says it should be? So if the put price is $3, it is too high relative to the call price. An arbitrager should buy the call, short the put, and short the stock. This generates -2 plus 3 plus 29, which is $30 in cash, which is invested at 10%. Regardless of what happens, a profit with a present value of 3 minus 2.51, which is 49 cents, is locked in. If the stock price is above $30 in 6 months, the call option is exercised and the put option expires worthless. The call option enables the stock to be bought for $30, or 30 e to the minus 0.10 times 6/12, which is $28.54 in present value terms. The dividends on the short position cost 0.5 e to the minus 0.1 times 2/12, plus 0.5 e to the minus 0.1 5/12, which is 97 cents in present value terms, so that there is a profit with a present value of $30 minus 28.54 minus 0.97, which is 0.49. If the stock price is below $30 in 6 months, the put option is exercised and the call option expires worthless. The short put option leads to the stock being bought for $30, which is in present value terms 28.54. The dividends on the short position cost 97 cents again in present value terms, so that there is a profit with a present value of 30 minus 28.54 minus 0.97, which leads to 49 cents once again. So problem 1116, the price of an American call on a dividend paying stock is $4. The stock price is $31, the strike price is $30, and the expiration date is in 3 months. The risk-free interest rate is 8%. Derive upper and lower bounds for the price of an American put on the same stock with the same strike price and expiration date. And of course, we know that upper and lower bounds are given from equation 11.7. We can remember equation 11.7, go to the book. And there is 11.7. Basically, it's an upper and a lower bound that refers to the difference between the American call and the American put. We see that the American call minus the American put is bounded below by S0 minus K, the strike price. And it's bounded above by S0 minus the present value of K, which is e to the minus RT. So, okay, we stop sharing. We stop sharing and hold on a second. We go back. This is equation 11.7 once again. And so we have upper and lower bounds. In this case, 4 minus the put. So it's $4 for the call minus the put is 31 minus 30, bounded below by 31 minus 30, and bounded above by 31 minus present value of 30, which is 0.08 times 1/4, because the expiration date is in 3 months. And so you obtain these upper and lower bounds for the put. So upper and lower bounds for the American put are therefore $2.41 and $3. Let's go through the next problem, which is interesting. Explain carefully the arbitrage opportunities in problem 1116, the previous problem, if the American put price is greater than the calculated upper bound. If the American put price is greater than $3, an arbitrager can sell the American put and short the stock and buy the American call. This realizes an immediate income of $3 plus $31 minus 4, which is $30, which can be invested at the risk-free interest rate. At some stage during the 3-month period, either the American put or the American call will be exercised. The arbitrager then pays $30, receives the stock, and closes out the short position. The cash flows to the arbitrager are $30 at time 0 and minus $30 at some future time. These cash flows have a positive present value. So the next problem, which is 1118, prove the result in equation 11.7. For the first part of the relationship, consider a portfolio consisting of a European call plus an amount of cash equal to K, and B, a portfolio consisting of an American put plus one share. As in the text, we use C, lowercase c and P to denote the European call and put option price, and capital C and capital P to denote the American call and put option prices. Because the American put is always greater or equal than the European, it follows from put call parity that the American put option is worth at least as much as C plus K to the minus RT minus S0. And since C is equal to capital C, the American call and the European call are worth the same because it's a non-dividend paying stock. Then you have P greater or equal to C plus K to the minus RT minus S0. So finally you obtain call minus put is bounded above by S0 minus K to the minus RT. For a further relationship between C and P, consider portfolio I, one European call option plus an amount of cash equal to K, one American put option plus one share. Both options have the same exercise price and expiration date. Assume that the cash in portfolio I is invested at the risk-free interest rate. If the put option is not exercised early, portfolio J is worth maximum of ST and K at time T. Portfolio I is worth one European call plus one, an amount of cash equal to K is max of ST minus K and 0 and K to the minus RT, which makes it equal to max of ST and K minus K plus K to the minus RT. At this time, portfolio I is therefore worth more than portfolio J. Suppose next that the put option in portfolio J is exercised early, say at time tau. This means that portfolio J is worth K at time tau. However, even if the call were worthless, portfolio I would be worth K to the minus R tau at time tau. It follows that portfolio I is worth at least as much as portfolio J in all circumstances. Hence, C plus K is greater than or equal to P plus S0. And since lowercase c is equal to uppercase C, European call is equal to American call, you obtain C plus K is greater or equal to P plus 0, or C minus P is greater than or equal to S0 minus K, and you have managed to, of course, obtain the lower bound in this relationship. So combining this with the other inequality, we obtain basically equation 2.11, whatever it was, 2.11.7, excuse me. So the next question is asking you to prove the result in equation 1111. So let's go to equation 1111 and remember what 1111 is. So there is 1111. So it's basically the upper and lower bounds for the difference between the American call and the American put in the case that dividends are allowed. So let's just look at it one more time. It's right here. C minus P is lower bounded by S0 minus D minus K and upper bounded by S0 minus K minus e to the RT. So now that we know this, let's go and try to prove it. Okay. So hint, for the first part of the relationship, we consider a portfolio consisting of a European call plus an amount of cash equal to D plus K, and B, a portfolio consisting of an American put plus one share. As in the text, we use C and P to denote the European call and put price options, and C and capital C and P to denote the American call and put option prices. The present value of the dividends will be denoted by D. As shown in the answer to problem 1118, when there are no dividends, we have this relationship, this upper bound. So dividends reduce C and increase P. Hence, this relationship must also be true when there are dividends. That's true. Okay, so this upper bound is established already. For a further relationship between C and P, consider portfolio I, one European call plus an amount of cash equal to D plus K, and portfolio J, one American put option plus one share. Both options have the same exercise price and expiration date. Assume that the cash in portfolio I is invested at the risk-free interest rate. If the put option is not exercised early, portfolio J is worth the max of STK plus D to the RT at time capital T. Portfolio I is worth the maximum of ST minus K and 0, and the value of the cash, which is D plus K, accumulated to time capital T. So that gives max ST minus K, ST and K, DE to the RT plus K to the RT minus K. So what you've done here is basically you plus K and minus K. So portfolio I is therefore worth more than portfolio J. So for sure. Suppose next that the put option in portfolio J is exercised early, say at time tau. This means that portfolio J is worth at most K plus D to the R capital E to the R tau at time tau. However, even if the call option were worthless, portfolio I would be worth D plus K E to the R tau at time tau. It follows that portfolio I is worth more than portfolio J's in all circumstances. And hence we obtain that C plus D plus K is an upper bound to P plus S0. And since the call option, American call option is at least as much as the European call option, you see here it's an inequality because this is a dividend paying stock. So the American call is basically worth at least as much as the European call. And so this is C minus P is greater than or equal to S0 minus D minus K. Okay. So consider a 5-year call option on a non-dividend paying stock granted to employees. The option can be exercised at any time after the end of the first year. Unlike a regular exchange traded call option, the employee stock option cannot be sold. What is the likely impact of this restriction on early exercise? So what's the answer to that? An employee stock option may be exercised early because the employee needs cash or because he or she is uncertain about the company's future prospects. Regular call options can be sold in the market in either of these two situations, but employee stock options cannot be sold. In theory, an employee can short the company's stock as an alternative to exercising. In practice, this is not usually encouraged and may even be illegal for senior managers. These points are discussed further in chapter 16. Okay, we're not going to get there, but that's fine. Let's go to problem 22. What is the impact, if any, of negative interest rates on the put-call parity result for European options, and the result that American call options on non-dividend paying stocks should never be exercised early, and the result that American put options on non-dividend paying stocks should sometimes be exercised early? Assume that holding cash earning zero interest is not possible. The put-call parity result still holds. The arguments are unchanged. Deep in the money, American calls might be exercised early because option holder will prefer to pay the strike price earlier. Okay, so the result, so this was for the first one was the put-call parity result for European options. The put-call parity result still holds. The arguments are unchanged. And for the result that American call options on non-dividend paying stocks should never be exercised early. Deep in the money, American calls might be exercised early because option holder will prefer to pay the strike price earlier. And so that's how that result is impacted. The result that American put options on non-dividend paying stocks should sometimes be exercised early. Deep in the money, American puts should not be exercised early because the holder would rather delay receiving the strike price. I think there's a mistake here. I'm not sure. I'm not exactly sure if I agree with this discussion, but that's okay. I leave it for now. We go to chapter 2 of Stephen Shreve. Okay. So this is the binomial asset pricing model, and we're gonna go through exercise. Give me one moment. Exercise 1.4. In the proof of theorem 1.2.2, show that under the deduction hypothesis that xn plus 1 omega 1 through omega n t is vn plus 1 omega 1 through omega n t. And the proof is xn plus 1 is delta n d Sn plus 1 plus r xn minus delta n Sn. Okay, so this is equal to delta n Sn d minus 1 minus r plus 1 plus r vn. And so this makes it equal to vn plus 1 h minus vn plus 1 t over u minus d, that's delta n. delta n times Sn. That gets multiplied by, so delta n times Sn is Vn plus 1 H minus Vn plus 1 T over U minus D times D minus 1 minus R plus 1 plus R. And then this I can write as P tilde plus Q tilde of P tilde Vn plus 1 H plus Q tilde Vn plus 1 T over 1 plus R. That's what Vn is. And so now I can just pull out all the terms with P tilde Vn plus 1 minus Vn plus 1 T. I'm sorry, what is happening here? That's right. So this is P tilde Vn plus 1 minus Vn plus 1 T minus Vn plus 1 H plus P tilde Vn plus 1 H plus Q tilde Vn plus 1 T. This is because D minus 1 minus R over U minus D is equal to minus P tilde. So then you obtain P tilde Vn plus 1 T plus Q tilde Vn plus 1 T. Okay. And that's Vn plus 1 T. There is exercise 1.8, the Asian option. So we consider the 3-period model of example 1.3.1 with S0 equal to 4, U equal to 2, and D equal to 1/2, and take the interest rate R to be 1/4, so that P tilde is equal to Q tilde equal to 1/2. For n equals 0, 1, 2, 3, we define Yn to be the sum of Sk, k equals 0 to n, to be the sum of the stock prices between times 0 and n. We consider an Asian call option that expires at time 3 and has strike price of k. This is like a European call, except the payoff of the option is based on the average stock price rather than the final stock price. So you let Vn of Sy denote the price of this option at time n, if Sn is equal to little s and Yn is equal to little y. In particular, V3 Sy is equal to 1/4 y minus 4 positive part. So develop an algorithm for computing Vn recursively, in particular, write a formula for Vn in terms of Vn plus 1. So you can do that because Vn of Sy is going to be 1 over 1 plus R, P tilde Vn plus 1 US, right? If the stock goes up, and Y plus US if the stock goes up. So if the sum is Y at time n, the sum will be Y plus US at time n plus 1 if the stock goes up, and it will be Y plus DS if the stock goes down. So plus Q tilde Vn plus 1 DS, Y plus DS, and so you obtain basically by doing the right substitutions, basically you obtain U is 2, D is 1/2, and so that's what it is. And then this is 2 over 5 because P tilde is 1/2 and Q tilde is 1/2, and 1 plus 1/4 in a denominator. So you obtain 2/5. So you apply the algorithm developed in one to compute V044, the price of the Asian option at time 0. And you obtain, so S3 of HHH is 32, Y3 of HHH is 60, V3 at 3260 is 11. And you apply this formula basically to go back. V2 of 16 and 28 is just basically 2/5 Vn plus 1, 2s, y plus 2s, which is V3 of 32 and 60, plus V3 of 8, 36, and that's how you obtain V2. And then to obtain V1, you take V2 of 16, 28 and V2 of 4, 16, put them in this formula, and you obtain V1 of 8, 12. And to obtain V2 of 4, 16, you obtain it by basically applying this formula to V3 of 8, 24. So it's 2/5 of V3 8, 24 plus V3 of 218. That makes it 1, etc. And so it's computed recursively from the end to the, from right to left, if you like, by using exactly this recursive formula. And that's that. You provide the formula for delta n of Sy, the number of shares of stock that should be held by the replicating portfolio at time n, if Sn is equal to S and Yn is equal to Y. Well, we know that delta n of Sy is Vn plus 1 US, Y plus US, minus Vn plus 1 ds, Y plus ds, over U minus ds. Okay, and this is where I conclude part 3 of STAT 761. This is the end of the exercise session. I wish you good luck for your final. And if you have any questions, you know where to find me. It's always 8 to 9 a.m. on Tuesday morning.